Deep in the cosmic void, a visitor hurtles through the darkness between stars. 7 miles wide, composed of pristine ice older than Earth itself, it follows a trajectory so statistically improbable that it defies natural explanation. Its surface, sculpted by eons of cosmic radiation, glimmers faintly under the distant glow of stars, a silent traveller bearing secrets from beyond our solar system. Its path will take it past Mars, behind the Sun, near Earth, and through Jupiter's magnetosphere, a sequence that reads like a reconnaissance mission. Astronomers calculate its velocity at a staggering 196,000 miles per hour, making it one of the fastest objects ever observed in our celestial neighborhood. Every story like this begins quietly, just a strange light, a missing piece, a question no one wants to ask. If you feel that same tension, that pull towards something we're not supposed to see, hit like, subscribe, and comment your thoughts. And if you want others to join us on this journey, share the video, X, Facebook, Reddit, anywhere you can. You're the reason stories like this reach beyond the algorithm. Thank you for being awake. This trajectory, combined with its interstellar origin, has sparked intense debate within the scientific community. Is this object named 3I Atlas a natural wanderer, or something far more extraordinary? Its composition of ancient ice suggests it formed in the frigid outer reaches of another star system, where temperatures plummet to 400-degree domains. Yet its path is not random. It aligns with key celestial bodies in our solar system, almost as if guided by an unseen hand. Tonight we embark on an unprecedented journey to unravel the mysteries of our most enigmatic interstellar visitor. As it approaches perihelion, the point closest to the Sun, its icy surface will begin to vaporize, potentially revealing layers of material untouched since the dawn of its creation. The truth about 3I Atlas may reshape our understanding of life in the universe. Prepare yourselves. We begin. Part 1. The Discovery. What if the next great discovery in astronomy arrived disguised as just another faint point of light moving against the stars? On July 1st, 2025, at the Atlas Observatory in Rio Hurtado, Chile, automated systems detected a faint point of light moving against the background stars. Designated A11PI3Z, this object initially seemed unremarkable, just another moving speck in the night sky. But as observations accumulated, its true significance emerged. By July 6th, astronomers confirmed the impossible. A11PI3Z was not a local asteroid or comet. It was the third confirmed interstellar object to visit our solar system, and it was unlike anything we had ever seen. The discovery of 3I Atlas, as it was later named, was not a dramatic revelation but a testament to the methodical patience of modern astronomy. The Atlas system, funded by NASA and operated by the University of Hawaii, was designed to detect potentially hazardous asteroids. Its 4 telescopes, strategically positioned around the globe, scan vast swaths of sky every clear night. But this time, Atlas detected something far more extraordinary, a visitor from another star system. 3I Atlas was faint, roughly magnitude 19, far too dim for amateur telescopes. Its slow motion against the stellar background suggested it was distant, approximately 5.2 astronomical units from the Sun. About the same distance as Jupiter. Yet, as telescopes around the world began tracking the object, its true nature became clear. It was moving on a hyperbolic trajectory, entering our solar system from interstellar space and destined to depart, never to return. The confirmation process was complex. Orbital eccentricity, the key measurement, had to be determined with precision. Objects with eccentricities greater than 1 follow hyperbolic trajectories. Indicating interstellar origins, 3I Atlas fit this profile perfectly. But atmospheric turbulence, instrumental errors, and the object's faintness introduced uncertainties. It took multiple nights of precise astrometry to eliminate any doubt. By July 6th, the world knew 3I Atlas was the third interstellar visitor to grace our solar system. The astronomical community's reaction was immediate and intense, unlike the surprise discovery of Oumuamua. In 2017, which caught researchers off guard, the scientific world had been preparing for additional interstellar visitors. Observation protocols were established, theoretical frameworks were developed, and funding mechanisms were in place for rapid follow-up. Dr. Robert Werrick, who discovered Oumuamua 8 years earlier, commented that the detection of 3I Atlas felt both familiar and entirely new. The methodical process of confirmation was similar. But the object itself promised to be far more accessible to detailed study. Unlike Oumuamua, which was already on its outbound journey when discovered, 3I Atlas was still approaching the Sun, offering months of observation opportunities. The stage was set for one of the most intensive astronomical observation campaigns in history. But as the world turned its telescopes toward this enigmatic visitor, questions began to emerge. Was 3I Atlas simply a natural interstellar comet, or was it something far more extraordinary? The answers, hidden in its trajectory and composition, would challenge our understanding of the cosmos and our place within it. It's known, 3I Atlas is a 7-mile-wide interstellar object on a hyperbolic trajectory. Unknown, its precise origin, composition, and the reason for its statistically improbable path, as 3I Atlas continues its journey toward perihelion. On October 29, 2025, the countdown begins to unravel its mysteries. Part 2. The Black Forest Theory. What if the silence of the universe is not a sign of emptiness, but of civilizations hiding in the cosmic dark? The Black Forest Theory, popularized by Chinese science fiction author Liu Cixin in his acclaimed three-body problem trilogy, offers a chilling explanation for the Fermi paradox, the contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for their existence. The theory suggests that advanced civilizations remain deliberately hidden, using sophisticated probes disguised as ordinary space debris to study developing worlds like Earth. In this cosmic forest, silence equals survival, while detection means destruction. Under the Black Forest theory, civilizations develop extensive passive surveillance networks, employing probes that appear natural to avoid detection. These reconnaissance systems masquerade as asteroids, comets, or other innocuous space debris, allowing advanced civilizations to gather intelligence about potential threats while maintaining their own concealment. The theory assumes that survival is the primary goal of any civilization, and that technological advancement inevitably leads to the capability for interstellar destruction. In this cosmic Mexican standoff, every civilization remains silent and hidden, desperately trying to detect others before being detected themselves. In the context of 3I Atlas, the Black Forest theory provides a framework for interpreting its unusual characteristics and trajectory. If the theory is correct, then what we interpret as an interstellar comet might actually be a sophisticated surveillance probe designed to study our solar system while maintaining perfect camouflage as a natural object. The size of 3I Atlas, 7 miles wide, becomes particularly significant. Under this interpretation, Such an object provides ample space for concealing advanced instrumentation, power systems, and data processing capabilities while maintaining the external appearance of a natural comet. Its large mass would also provide excellent shielding against cosmic radiation and solar heating, protecting sensitive electronics during the long journey between star systems. The trajectory of 3I Atlas aligns remarkably well with what a dark forest reconnaissance mission might attempt to accomplish. Its carefully orchestrated sequence of planetary flybys maximizes observational opportunities while minimizing the risk of detection. The timing of perihelion on the far side of the Sun from Earth creates a natural period of concealment during which any artificial systems could operate without risk of observation from our most sensitive instruments. The pristine composition detected in 3I Atlas could represent either genuine ancient materials preserved from another star system or sophisticated mimicry designed to fool spectroscopic analysis. But the Black Forest theory is not without criticism. It assumes that all civilizations develop along similar technological and sociological paths, which may not reflect the true diversity of possible evolutionary outcomes. It also assumes that interstellar destruction is both feasible and preferable to other forms of interaction, which remains speculative given our limited understanding of advanced technology. Furthermore, the theory relies heavily on game theory assumptions that may not apply to alien psychology or decision-making processes. Human concepts of threat assessment, risk management, and strategic thinking might be completely irrelevant to genuinely alien intelligences that evolved under different environmental and evolutionary pressures. Despite these criticisms, the Black Forest theory remains compelling because it provides a coherent explanation for both the Fermi paradox and the unusual characteristics of objects like 3I Atlas. It suggests that the universe might be teeming with intelligent life, but that this life remains hidden behind veils of technological sophistication that make it virtually undetectable to less advanced civilizations. As 3I Atlas continues its journey through our solar system, the Black Forest theory offers a lens through which to evaluate its anomalous observations. Could this enigmatic visitor be more than it seems? The answer may lie in the data gathered during its upcoming flybys and perihelion passage. Known, 3I Atlas follows a trajectory that aligns with the reconnaissance goals predicted by the Black Forest theory. Unknown, whether its unusual characteristics are the result of natural processes or artificial design. As 3I Atlas approaches its Mars flyby on October 3, 2025, the opportunity to gather crucial data draws near. Part 3. The Mars Encounter. What if our first close look at 3I Atlas reveals more questions than answers? On October 3, 2025, 3I Atlas will make its first major flyby, passing within 18 million miles of Mars. This encounter will occur during the Martian dawn, providing optimal lighting conditions for both orbital and surface-based observations. Multiple spacecraft currently operating in Mars orbit will have unprecedented access to the object during this flyby. NASA's MAVEN mission, designed to study the Martian upper atmosphere, will be able to detect any gas emissions from 3I Atlas using its suite of spectrometers. The European Space Agency's Mars Express orbiter will contribute high-resolution imaging capabilities, while China's Tianwen-1 orbiter will provide additional observational perspectives. Ground-based observers on Mars, including NASA's Perseverance and Curiosity rovers, may be able to image the object if atmospheric conditions permit. The Mars encounter is particularly significant because it occurs while 3I Atlas is still approaching the Sun and before significant cometary activity is expected to begin. Any coma or tail development detected during this period would suggest either unusual composition or artificial outgassing mechanisms. Natural comets typically do not develop visible comae until they approach within 2 to 3 astronomical units of the Sun. The expected angular size of 3I Atlas during the Mars flyby will allow for unprecedented detail in imaging studies. If the object maintains its estimated 7-mile diameter, it should appear as a resolved disk in high-resolution observations, potentially revealing surface features, rotation characteristics, and any asymmetric outgassing patterns. However, the Mars flyby is just the beginning, as 3I Atlas continues its journey. It will approach perihelion on October 29, 2025, at a distance of 1.36 astronomical units from the Sun. This closest approach will subject the object to maximum solar heating, potentially revealing its true nature. If 3I Atlas is a natural comet, maximum coma development and tail formation should occur during this period. The absence of expected cometary activity or the presence of unusual emission patterns could support more exotic explanations. For the object's origin, known 3I Atlas will pass within 18 million miles of Mars on October 3, 2025. Unknown whether it will exhibit cometary activity or reveal artificial characteristics during this encounter. As the Martian dawn illuminates 3I Atlas, the world watches and waits. Part 4. The size of 3I Atlas. What if the sheer scale of 3I Atlas is its most telling feature? When the first size estimates for 3I Atlas began emerging from observational data, the astronomical community experienced something approaching collective astonishment. Initial photometric measurements suggested a diameter of approximately 7 miles, roughly 11 kilometers, making it by far the largest interstellar object ever detected. To put this size in perspective, Oumuamua, our first interstellar visitor, measured roughly 400 meters in length and perhaps 40 meters in width. Borisov, our second interstellar visitor, was even smaller, with a nucleus estimated at less than 1 kilometer in diameter. 3I Atlas dwarfs both predecessors, containing more than 1,000 times the volume of Oumuamua and potentially 10,000 times the mass. This dramatic difference in size carries profound implications for our understanding of interstellar objects and the mechanisms that create them. Smaller objects like Oumuamua and Borisov could easily be explained as fragments ejected during planetary formation processes or gravitational interactions within their home systems. Large objects like 3I Atlas require more dramatic explanations. Perhaps the disruption of a dwarf planet, the gravitational ejection of a small moon, or the catastrophic breakup of a massive comet. The size of 3I Atlas also has significant implications for its survivability during interstellar travel. Space between the stars is not truly empty but contains a thin medium of gas and dust, cosmic radiation, and occasional encounters with other objects. Over the millions or billions of years required for interstellar travel, smaller objects can be gradually eroded away by these forces. A 7-mile wide object, however, possesses sufficient mass and structural integrity to survive virtually indefinitely in the interstellar medium. Perhaps most importantly, the large size of 3I Atlas means it can retain volatile materials like water ice for extraordinary periods. Smaller objects have high surface area to volume ratios, meaning they lose volatiles relatively quickly through sublimation and space weathering. A large object like 3I Atlas, however, can maintain a pristine interior for billions of years, effectively serving as a time capsule, preserving conditions from its original stellar system. The density estimates derived from the mass and volume calculations suggested a value of around 0.6 grams per cubic centimetre, significantly less than solid rock but consistent with a mixture of water ice, organic compounds and rocky minerals. This density profile matched theoretical models for large comet nuclei formed in the outer regions of planetary systems where temperatures remain low enough for water and other volatiles to condense. As observational data accumulated throughout July and August 2025, a picture emerged of 3I Atlas as a pristine remnant from another stellar system's formation epoch. Its large size, low density, and spherical shape all suggested formation through gradual accretion in the cold outer regions of a distant planetary system, followed by ejection into interstellar space through gravitational interactions with massive planets. But the story of 3I Atlas is far from complete. As more sophisticated observations began revealing details about the object's composition and trajectory, questions arose that challenged simple explanations and opened the door to far more exotic possibilities. Known, 3I Atlas is approximately 7 miles in diameter with a density consistent with a mixture of ice and rock. Unknown, the exact mechanism that ejected it from its home system and the full extent of its internal composition. As 3I Atlas approaches perihelion, the true nature of this enigmatic visitor may finally be revealed. Part 5. The composition of 3I Atlas. What if the pristine materials of 3I Atlas tell a story of another star? The composition of 3I Atlas represents one of the most significant discoveries in interstellar object research, providing unprecedented insights into the chemistry and formation processes of a distant stellar system. As the object approached the Sun throughout the summer of 2025, increasingly powerful telescopes turned their attention to deciphering the spectroscopic signatures hidden in its faint reflected light. The first breakthrough came from observations made with the NASA Infrared Telescope facility on Mauna Kea, Hawaii. Using its high-resolution spectrometer, astronomers detected strong absorption features consistent with water ice across multiple infrared wavelengths. This discovery wasn't entirely surprising. Water ice is common in comets throughout our solar system, but the characteristics of this ice told a remarkable story. Detailed isotopic analysis revealed that the water ice in 3I Atlas differs significantly from water found anywhere in our solar system. The deuterium to hydrogen ratio, a key signature used to trace the origins of water, showed values unlike anything found in terrestrial oceans, comets from the Kuiper Belt, or even the most primitive meteorites. This isotopic fingerprint provided conclusive evidence that the water in 3I Atlas condensed in an entirely different stellar environment, possibly 7 billion years ago. The pristine nature of this ancient water ice cannot be overstated in its scientific importance. Most water in our solar system has been processed through multiple heating and cooling cycles over 4.6 billion years. Comets that approached the Sun lose surface layers through sublimation, while water in asteroids and planets has been altered by thermal and chemical processes. The water in 3I Atlas, however, appears to have remained frozen and unaltered since its original formation, preserving a direct record of conditions in its birth system. Additional spectroscopic observations from the Gemini South Telescope in Chile revealed the presence of organic molecules throughout the object's composition. Complex hydrocarbons including methane, ethane, and more sophisticated organic compounds. were detected alongside the water ice. These molecules suggested that 3I Atlas formed in a region rich in carbon and other heavy elements, possibly around a star with a different metallicity than our own Sun. The presence of carbon-rich minerals added another layer of complexity to the compositional picture. Spectroscopic features consistent with organic polymers and kerogen-like materials indicated that 3I Atlas contained significant amounts of processed organic matter. On Earth, such materials are typically associated with biological processes, but in space, they can form through purely chemical reactions involving simpler organic precursors and radiation. Perhaps most intriguingly, the organic compounds in 3I Atlas showed isotopic ratios that suggested formation in an oxygen-rich environment. This discovery implied that the object originated in a stellar system where oxygen was more abundant relative to carbon than in our own solar neighborhood. Such conditions could arise around older stars that have undergone multiple generations of nuclear synthesis, enriching their surrounding protoplanetary disks with heavy elements. Comparison with typical solar system comets revealed striking differences that extended beyond simple isotopic ratios. Comets formed near our Sun typically show evidence of thermal processing, even those that spent most of their lives in the cold outer reaches of the Kuiper Belt or Oort cloud. They contain minerals that could only form at high temperatures, suggesting they incorporated material that once resided close to the proto-Sun before being transported outward. 3I Atlas, however, showed no evidence of such thermal processing. Its mineral composition appeared consistent with condensation at extremely low temperatures, possibly below 30 Kelvin. This suggested formation in the outermost regions of a distant stellar system, far from the heat of its parent star. The scientific value of this pristine composition extends far beyond simple curiosity about distant worlds. 3I Atlas represents a direct sample of protoplanetary disk material from another star, allowing astronomers to test theoretical models of planet formation under different chemical and physical conditions. The object serves as a natural laboratory for studying how stellar metallicity, disk dynamics, and other factors influence the types of materials available for planet construction. The detection of complex organic molecules also has profound implications for astrobiology. While these compounds could form through non-biological processes, their presence in a pristine interstellar object demonstrates that the chemical precursors for life can form and survive over cosmic timescales. This finding supports the concept that organic chemistry is a natural consequence of stellar and planetary formation processes throughout the galaxy. Known: 3I Atlas contains pristine water ice and complex organic molecules with isotopic ratios unlike anything in our solar system. Unknown: the exact conditions under which these materials formed, and whether they bear signatures of biological processes. As 3I Atlas continues its journey, the secrets locked within its composition may reshape our understanding of life in the universe. Part 6. The trajectory of 3I Atlas. What if the path of 3I Atlas is too precise to be natural? The orbital path of 3I Atlas through our solar system represents one of the most statistically improbable trajectories ever recorded for a celestial object. As astronomers refined their calculations throughout the summer of 2025, the mathematical precision of the object's route began to raise questions that challenged conventional explanations of natural orbital mechanics. 3I Atlas approaches our solar system on a steep retrograde orbit, meaning it travels in the opposite direction to the planet's orbital motion around the Sun. This retrograde trajectory itself isn't unusual for interstellar objects, as visitors from other star systems can approach from any direction in three-dimensional space. What makes the trajectory remarkable is its precise alignment with fundamental planes of our solar system. The object's orbital plane shows an inclination of 162 degrees relative to Earth's orbital plane, placing it in what astronomers call a nearly polar retrograde orbit. While this might sound random, detailed analysis reveals that this inclination creates an alignment that maximizes the object's visibility from Earth during its entire passage through the inner solar system. By pure coincidence, 3i Atlas will remain observable from Earth-based telescopes throughout its entire visit, never disappearing behind the Sun for extended periods, as most objects do. The trajectory includes a series of planetary encounters that seem almost choreographed for maximum scientific observation opportunities. On October 3, 2025, 3i Atlas will pass within 18 million miles of Mars, close enough for detailed observation by multiple spacecraft currently orbiting the red planet. The timing places this encounter during Martian dawn, when observing conditions will be optimal for detecting any coma or tail development as the object approaches its closest point to the Sun. Following the Mars encounter, 3i Atlas will reach perihelion on October 29, 2025, at a distance of 1.36 astronomical units from the Sun. This perihelion distance places the object just outside Earth's orbit, far enough to avoid significant gravitational perturbation, but close enough for maximum solar heating and potential coma development. The timing of perihelion on the far side of the Sun from Earth creates a natural observational challenge that can only be overcome by spacecraft positioned at the L1 Lagrange point or in Mars orbit. The post-perihelion trajectory continues the pattern of seemingly optimized planetary encounters. On December 19, 2025, 3i Atlas will pass approximately 170 million miles from Earth, close enough for detailed observation. With the James Webb Space Telescope and the Vera C. Rubin Observatory, but far enough to avoid any gravitational influence on either the object or our planet. The most remarkable encounter occurs on March 16, 2026, when 3i Atlas will pass just 33 million miles above Jupiter's cloud tops. This distance places the object well within Jupiter's magnetosphere and close enough for potential sample collection by the Juno spacecraft. Statistical analysis of this trajectory reveals probabilities so low they challenge conventional assumptions about random orbital mechanics. The precise alignment with Earth's orbital plane has less than a 0.2% probability of occurring by chance. When combined with the specific planetary encounter distances and timing, the overall probability drops to approximately 1 in 20,000 TOS, statistically significant enough to warrant serious consideration of non-random explanations. The trajectory also exhibits characteristics that would be ideal for a reconnaissance mission designed to study our solar system's major planets. The sequence of encounters allows for detailed observation of Mars, optimal solar approach for instrument calibration and power generation, strategic positioning relative to Earth for communication or observation, and close approach to Jupiter for sampling of the solar system's largest planetary magnetosphere. If 3i Atlas were an artificial probe designed to study our solar system, its trajectory would be difficult to improve upon. But the debate over the trajectory's significance is far from settled. Critics argue that confirmation bias might be influencing the interpretation of what could simply be a remarkable coincidence. With billions of objects in the galaxy and countless possible trajectories, even extremely improbable events must occasionally occur. The human tendency to see patterns and purpose in random events might be creating artificial significance where none actually exists. However, the mathematical reality of the trajectory's precision is difficult to dismiss. Whether the product of cosmic coincidence or intelligent design, the path of 3i Atlas through our solar system represents one of the most precisely orchestrated celestial mechanics displays ever observed. Known. The trajectory of 3i Atlas is statistically improbable and aligns with optimal observation conditions for multiple planets. Unknown. Whether this alignment is the result of natural chance or deliberate design. As 3i Atlas approaches perihelion, the true nature of its remarkable trajectory may finally be revealed. Part 7. The velocity of 3i Atlas. What if the speed of 3i Atlas defies natural explanation? One of the most striking characteristics of 3i Atlas is its velocity relative to the Sun. The object approaches our solar system at approximately 33 kilometers per second, significantly faster than most natural interstellar objects. Objects ejected from nearby star systems typically arrive with lower velocities, between 20 and 30 kilometers per second, due to the gravitational influence of the Milky Way's stellar population. The high velocity of 3i Atlas implies either an origin from a very distant stellar system or artificial acceleration beyond what natural gravitational slingshot effects could produce. The retrograde nature of 3i Atlas's orbit also enables efficient sampling of solar system material that would be difficult to achieve with a prograde trajectory. As 3i Atlas moves against the general flow of solar system material, it encounters a higher flux of dust, charged particles and other debris that could provide information about the chemical and physical properties of our star system. Gravitational modeling of the trajectory reveals another intriguing characteristic. The path appears to be carefully optimized to avoid close encounters with the outer planets during the approach phase. Saturn, Uranus, and Neptune are all positioned such that their gravitational influences on 3i Atlas are minimized, preventing significant trajectory modifications that might alter the carefully choreographed sequence of inner system encounters. The high incoming velocity of 3i Atlas raises questions about its origin and the mechanisms that propelled it to such speeds. Natural gravitational slingshot effects, where an object gains velocity through close encounters with massive planets or stars, can explain some high-velocity interstellar objects. However, the precision of 3i Atlas's trajectory suggests a level of control that goes beyond random gravitational interactions. If the object were artificially accelerated, its creators would need advanced propulsion technologies capable of achieving and maintaining such high velocities over interstellar distances. Critics of the artificial origin hypothesis point out that the high velocity could simply be the result of a rare but natural event, such as a close encounter with a massive star or a supernova explosion. Such events could impart significant velocity to an object, ejecting it from its home system at speeds far exceeding typical interstellar velocities. However, the statistical improbability of such an event occurring in just the right way to produce the precise trajectory of 3i Atlas raises questions about the likelihood of a natural explanation. Known. 3i Atlas is traveling at approximately 33 kilometers per second relative to the Sun. Unknown. Whether this velocity is the result of natural acceleration or artificial propulsion. As 3i Atlas continues its journey, the mystery of its velocity deepens. Part 8. The missing cometary signatures. What if 3i Atlas defies the rules of cometary behavior As 3I Atlas continues its approach toward the Sun, astronomers have been conducting intensive searches for the characteristic chemical signatures that should accompany a natural comet of this size as it begins to experience solar heating. Traditional comets formed in the cold outer regions of our solar system contain a mixture of water ice, frozen carbon dioxide, methane, ammonia, and various organic compounds. As these objects approach the Sun, solar radiation begins sublimating these volatile materials, creating the characteristic coma and tail that make comets visible to amateur observers. This process begins gradually at distances of 5 to 6 astronomical units from the Sun and intensifies dramatically as the comet approaches perihelion. The specific gases released during this sublimation process create distinctive spectroscopic signatures that serve as fingerprints for cometary composition. Among the most readily detectable are cyanogen, Cn, and diatomic carbon, C2, which produce strong emission lines in the visible spectrum when excited by solar ultraviolet radiation. These molecules are among the first to appear as a comet activates, typically becoming detectable while the object is still 3 to 4 astronomical units from the Sun. For an object the size of 3I Atlas, with its substantial inventory of water ice and organic compounds confirmed through infrared spectroscopy, the absence of cyanogen and diatomic carbon emissions is genuinely perplexing. By late August 2025, when the object reached approximately 2.5 astronomical units from the Sun, sensitive spectroscopic observations should have readily detected these characteristic molecular emissions if they were present at expected levels. Multiple observatories have conducted systematic searches for the missing signatures using increasingly sophisticated techniques. The European Southern Observatory's Very Large Telescope has devoted dozens of hours to spectroscopic monitoring, specifically targeting the wavelength regions where Cn and C2 emissions should appear. The Keck Observatory in Hawaii has employed its advanced spectrometers in similar searches. The results have been consistently negative. No detection of the expected cometary gases at any level approaching normal abundances. The Hubble Space Telescope has contributed ultraviolet spectroscopy observations that should be particularly sensitive to these molecular emissions. Hubble's ability to observe above Earth's atmosphere eliminates atmospheric interference that might mask weak emission lines in ground-based observations, despite multiple observation sessions specifically designed to detect early cometary activity. Hubble has found no evidence of cyanogen or diatomic carbon around 3I Atlas. Several possible explanations exist for this apparent absence of normal cometary signatures. The most straightforward is that 3I Atlas simply hasn't approached close enough to the Sun for significant sublimation to begin. Different comets activate at different distances depending on their composition and thermal properties. Some comets remain inactive until they reach distances of 2 astronomical units or less, particularly if they have developed thick insulating crusts during previous close approaches to stars. However, this explanation faces challenges when applied to 3I Atlas. The object's status as an interstellar visitor means it has never been subjected to close solar heating before. Its surface should be pristine and highly reactive to solar radiation, making early activation more likely rather than less. Additionally, the detection of water ice through infrared spectroscopy suggests that at least some of the object's volatile materials are already accessible at its current distance from the Sun. Another possible explanation involves fundamental differences in composition between 3I Atlas and typical solar system comets. The interstellar origin of the object means it formed in a different chemical environment. potentially around a star with different metallicity or under different temperature and pressure conditions. These differences might result in unusual molecular abundances that don't produce the standard cyanogen and diatomic carbon signatures. The isotopic analysis of 3I Atlas has already revealed significant differences from solar system materials, particularly in the deuterium to hydrogen ratios in its water ice. Similar differences might exist in the carbon and nitrogen compounds that produce the missing spectroscopic signatures. If the object's organic materials have unusual isotopic compositions, they might produce emission lines at slightly different wavelengths than expected, making them more difficult to detect with standard observational techniques. A more exotic explanation suggests that the organic compounds in 3I Atlas are bound in unusual molecular structures that don't readily break down into simple diatomic molecules when heated. Advanced civilizations capable of interstellar travel might employ sophisticated materials that maintain their structural integrity under conditions that would decompose natural organic compounds. Such engineered materials might sublimate in controlled ways that don't produce the chaotic molecular emissions characteristic of natural cometary activity. The possibility of active camouflage also deserves consideration. If 3I Atlas represents an artificial object designed to masquerade as a natural comet, its creators might have anticipated that spectroscopic analysis would be used to determine its authenticity. Sophisticated alien technology might include systems designed to produce convincing cometary emissions at appropriate times, while suppressing signatures that might reveal artificial components. Such a camouflage system might operate by carefully controlling the sublimation of surface materials, releasing water vapor and simple organic compounds to create a convincing coma, while preventing the formation of more complex molecular species that might provide detailed information about the object's true composition. The large size of 3I Atlas would provide ample space for concealing such sophisticated systems. Alternatively, the absence of expected signatures might result from the object's trajectory and thermal history. Unlike typical comets that approached the Sun from the cold outer solar system, 3I Atlas has been traveling through interstellar space for potentially millions of years. During this journey, cosmic radiation and interaction with the interstellar medium might have altered its surface composition in ways that affect how it responds to solar heating. Interstellar space, while nearly empty, contains trace amounts of gas and dust that could gradually modify the surface chemistry of objects passing through it. Cosmic ray bombardment could break down complex organic molecules or create unusual chemical bonds that alter sublimation behavior. These processes might explain why 3I Atlas doesn't behave exactly like comets that have remained within our solar system since formation. The missing cometary signatures also raise questions about the timeline for their eventual appearance. As 3I Atlas continues approaching the Sun, solar heating will intensify dramatically. Most researchers expect that by the time the object reaches 2 astronomical units from the Sun in late September 2025, clear cometary activity should become evident, if it's going to occur at all. The perihelion passage in late October represents the critical test for all theories about 3I Atlas's composition and nature. At 136 astronomical units from the Sun, the object will experience heating intense enough to sublimate virtually any volatile materials present in its composition. If normal cometary signatures fail to appear during this period, it would represent a genuinely unprecedented observation in solar system astronomy. Known: 3I Atlas has not exhibited the expected cometary signatures of cyanogen or diatomic carbon. Unknown: Weather. This absence is due to natural causes or artificial camouflage. As 3I Atlas approaches perihelion, the mystery of its missing cometary activity deepens. Part 9. The Perihelion Passage. What if perihelion reveals the true nature of 3I Atlas? The moment of greatest drama in 3I Atlas's journey occurs when it reaches perihelion at 136 astronomical units from the Sun on October 29, 2025. At this closest approach, the object will experience maximum solar heating, reaching temperatures sufficient to sublimate water ice and other volatiles from its surface. The object's velocity will peak at approximately 152,000 miles per hour relative to the Sun. Unfortunately for Earth-based observers, perihelion occurs when 3I Atlas is positioned on the far side of the Sun from our planet, hidden by solar glare and impossible to observe with ground-based telescopes. This timing creates both challenges and opportunities for the scientific community. The primary observational assets during perihelion will be spacecraft positioned at the L1 Lagrange point, approximately 1 million miles sunward of Earth, the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory will be able to monitor 3I Atlas as it rounds the Sun using coronagraphs designed to block the Sun's bright disk while revealing fainter objects in the surrounding corona. Mars-based observers will maintain their advantageous position during perihelion, as the red planet's orbital position places it roughly perpendicular to the Earth-Sun 3. I-Atlas alignment. This geometry means that spacecraft at Mars can observe 3I Atlas during its period of maximum solar heating without interference from solar glare. The perihelion passage represents the critical test for competing theories about 3I Atlas's nature. If the object is a natural comet, maximum coma development and tail formation should occur during this period. The absence of expected cometary activity or the presence of unusual emission patterns could support more exotic explanations for the object's origin. Solar heating during perihelion will also subject any artificial components to extreme thermal stress. Materials not designed for the space environment might fail catastrophically, while sophisticated alien technology might reveal itself through unexpected thermal signatures or controlled outgassing patterns. Known: 3I Atlas will reach perihelion on October 29, 2025, at 136 astronomical units from the Sun. Unknown whether it will exhibit cometary activity or reveal artificial characteristics during this critical period. As 3I Atlas approaches the Sun, the countdown to perihelion begins. Part 10. The December Earth Encounter. What if 3I Atlas reveals its secrets as it passes Earth? As 3I Atlas continues its outbound journey after perihelion, it reaches a significant milestone on December 19, 2025, when it passes approximately 170 million miles from Earth. This distance places the object just beyond Mars's orbital radius, making it accessible to Earth's most powerful telescopes while ensuring no gravitational interaction with our planet. The December 19th observation window is crucial because it represents the first opportunity for detailed Earth-based study of 3I Atlas after its perihelion passage. Any changes in the object's appearance, composition, or behavior caused by solar heating will be clearly visible during this period. The James Webb Space Telescope, JWST, will play a central role in these observations, using its unprecedented infrared sensitivity to analyze the chemical composition of any coma or tail that develops. JWST's spectroscopic capabilities can detect trace gases at concentrations far below the limits of ground-based instruments, potentially revealing exotic materials or unusual isotopic ratios that might indicate artificial origin. The Vera C. Rubin Observatory, with its enormous 8.4-meter primary mirror and state-of-the-art digital camera, will conduct intensive photometric monitoring to detect any subtle changes in the objects. Brightness or color that might indicate ongoing activity or structural modifications. The December observations are also significant because they occur during a period when 3I Atlas will be moving through the plane of the solar system, maximizing its interaction with solar wind particles and interplanetary dust. Any artificial systems designed to collect samples of solar system material would be most active during this phase of the trajectory. Ground-based radio telescopes will also focus on 3I Atlas during this period, searching for any electromagnetic emissions that might indicate active electronic systems. The object's distance will be optimal for radio observations, close enough for strong signal detection, but far enough to avoid interference from solar radio emissions. Known: 3I Atlas will pass approximately 170 million miles from Earth on December 19, 2025. Unknown. Whether it will exhibit unusual activity or emissions during this encounter. As 3I Atlas approaches Earth, the world prepares for a close look at this enigmatic visitor. Part 11. The Jupiter Flyby. What if Jupiter's magnetosphere reveals the truth about 3I Atlas? The most scientifically valuable encounter in 3I Atlas's journey occurs on March 16, 2026, when the object passes just 33 million miles above Jupiter's cloud tops. This close approach places 3I Atlas well within Jupiter's powerful magnetosphere, creating unique opportunities for both passive observation and active sampling. NASA's Juno spacecraft currently in orbit. Around Jupiter will be positioned to make detailed observations of 3I Atlas during the encounter. Juno's suite of instruments, designed to study Jupiter's interior structure and magnetic field, will be uniquely capable of detecting any interactions between the interstellar object and Jupiter's magnetosphere. The passage through Jupiter's magnetosphere will subject 3I Atlas to intense radiation and charged particle bombardment, any artificial. Systems would need sophisticated shielding to survive this environment. While natural materials might exhibit characteristic responses to the radiation exposure that could be detected by Juno's instruments, of particular interest is the possibility that Juno might be able to collect dust particles shed by 3I Atlas during the encounter. Jupiter's powerful magnetic field can trap charged dust particles, and Juno's dust detector might capture direct. Samples of interstellar material for the first time in human history. The gravitational interaction between 3I Atlas and Jupiter will also provide the final definitive measurement of the object's mass by precisely tracking how Jupiter's gravity affects the object's trajectory. Astronomers can calculate its mass with unprecedented accuracy, resolving remaining uncertainties about its density and internal structure. The Jupiter encounter represents the last major milestone in 3I Atlas's journey through our solar system. After this flyby, the object will begin its final departure into interstellar space, gradually fading from view as it moves beyond the reach of even our most powerful telescopes. Known: 3I Atlas will pass just 33 million miles above Jupiter's cloud tops on March 16, 2026. Unknown: whether it will exhibit unusual interactions with Jupiter's magnetosphere or reveal its true nature during this encounter. As 3I Atlas approaches Jupiter, the final chapter of its cosmic journey begins. Part 12. The dark forest hypothesis revisited. What if the dark forest theory explains the silence of the universe? The dark forest theory, popularized by Chinese science fiction author Liu Cixin, offers a chilling explanation for the Fermi paradox, the contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for their existence. The theory suggests that advanced civilizations remain deliberately hidden, using sophisticated probes disguised as ordinary space debris to study developing worlds like Earth. In this cosmic forest, silence equals survival, while detection means destruction. The theory assumes that survival is the primary goal of any civilization, and that technological advancement inevitably leads to the capability for interstellar destruction. In this cosmic Mexican standoff, every civilization remains silent and hidden, desperately trying to detect others before being detected themselves. In the context of Three-Eye Atlas, the dark forest theory provides a framework for interpreting its unusual characteristics and trajectory. If the theory is correct, then what we interpret as an interstellar comet might actually be a sophisticated surveillance probe designed to study our solar system while maintaining perfect camouflage as a natural object. The size of Three-Eye Atlas, 7 miles wide, becomes particularly significant under this interpretation. Such an object provides ample space for concealing advanced instrumentation, power systems, and data processing capabilities while maintaining the external appearance of a natural comet. Its large mass would also provide excellent shielding against cosmic radiation and solar heating, protecting sensitive electronics during the long journey between star systems. The trajectory of Three-Eye Atlas aligns remarkably well with what a dark forest reconnaissance mission might attempt to accomplish. Its carefully orchestrated sequence of planetary flybys maximizes observational opportunities while minimizing the risk of detection. The timing of perihelion on the far side of the Sun from Earth creates a natural period of concealment, during which any artificial systems could operate without risk of observation from our most sensitive instruments. The pristine composition detected in Three-Eye Atlas could represent either genuine ancient materials preserved from another star system or sophisticated mimicry designed to fool spectroscopic analysis. But the dark forest theory is not without criticism. It assumes that all civilizations develop along similar technological and sociological paths, which may not reflect the true diversity of possible evolutionary outcomes. It also assumes that interstellar destruction is both feasible and preferable to other forms of interaction, which remains speculative given our limited understanding of advanced technology. Furthermore, the theory relies heavily on game theory assumptions that may not apply to alien psychology or decision-making processes. Human concepts of threat assessment, risk management, and strategic thinking might be completely irrelevant to genuinely alien intelligences that evolved under different environmental and evolutionary pressures. Despite these criticisms, the dark forest theory remains compelling because it provides a coherent explanation for both the Fermi paradox and the unusual characteristics of objects like Three-Eye Atlas. It suggests that the universe might be teeming with intelligent life, but that this life remains hidden behind veils of technological sophistication that make it virtually undetectable to less advanced civilizations. As Three-Eye Atlas continues its journey through our solar system, the dark forest theory offers a lens through which to evaluate its anomalous observations. Could this enigmatic visitor be more than it seems? The answer may lie in the data gathered during its upcoming flybys and perihelion passage. Known The dark forest theory provides a framework for interpreting the unusual characteristics of 3I Atlas. Unknown whether the theory accurately describes the true state of galactic civilization. As 3I Atlas approaches its Mars flyby, the possibility of artificial origins looms large. Part 13. Dr. Avi Loeb and the Artificial Origin Hypothesis. What if one of astronomy's most controversial figures is right about 3I Atlas? Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and former chair of Harvard's Astronomy Department, has emerged as one of the most prominent and controversial voices in the search for evidence of extraterrestrial intelligence. His willingness to seriously consider artificial origins for unusual astronomical phenomena has sparked intense debate within the scientific community, nowhere more so than in his analysis of interstellar objects like Oumuamua and now 3I Atlas. Loeb's journey into the realm of controversial hypotheses began with Oumuamua, the first confirmed interstellar visitor to our solar system. When that cigar-shaped object exhibited unexplained acceleration away from the Sun, without showing any signs of cometary outgassing, most astronomers proposed various natural explanations involving exotic forms of sublimation or structural peculiarities. Loeb, however, took a different approach, suggesting that Oumuamua's behavior was consistent with artificial construction, specifically a light sail propelled by solar radiation pressure. This hypothesis, detailed in his book Extraterrestrial, the First Sign of Intelligent Life Beyond Earth, established Loeb as either a visionary willing to challenge conventional thinking, or a respected scientist who had ventured too far into speculative territory, depending on one's perspective. Regardless of the ultimate validity of his Oumuamua hypothesis, Loeb's approach demonstrated the importance of considering all possibilities when faced with genuinely anomalous observations. With the discovery of 3I Atlas, Loeb has once again stepped forward with hypotheses that challenge conventional interpretations, in a paper co-authored with Dr. Carson Eel of the Harvard-Smithsonian Center for Astrophysics. Loeb argues that 3I Atlas exhibits characteristics that are not only consistent with artificial construction, but may actually be more easily explained by technological rather than natural origins. The central pillar of Loeb's 3I Atlas hypothesis rests on the object's unprecedented size among interstellar visitors. At 7 miles in diameter, 3I Atlas is large enough to conceal virtually any form of advanced instrumentation while maintaining a convincing exterior appearance as a natural comet. Loeb argues that this size represents a Goldilocks zone for interstellar reconnaissance, large enough for sophisticated technology but not so large as to be obviously artificial. According to Loeb's analysis, the size of 3I Atlas provides several advantages that would be highly desirable for an artificial interstellar probe. First, the large mass provides excellent radiation shielding, protecting sensitive electronics during the potentially million-year journey between star systems. Second, the substantial volume allows for redundant systems and long-term power sources that could operate for geological timescales. Third, the size enables the probe to carry comprehensive analytical equipment for detailed study of target systems. Loeb also points to the object's high inbound velocity as evidence of possible artificial acceleration. At 33 kilometers per second relative to the Sun, 3I Atlas approaches faster than most natural interstellar objects, which typically arrive with velocities between 20 and 30 kilometers per second. While this difference might seem small, Loeb argues that it could indicate artificial acceleration beyond what natural gravitational slingshot effects could produce. The retrograde trajectory of 3I Atlas also features prominently in Loeb's hypothesis. While retrograde orbits are not unusual for interstellar objects, Loeb notes that this particular trajectory provides optimal conditions for comprehensive solar system reconnaissance. The retrograde motion maximizes the object's interaction with solar system material, while the specific orbital inclination ensures optimal visibility from multiple planetary systems throughout. The journey. Perhaps most significantly, Loeb emphasizes the statistical improbability of 3I Atlas's precise sequence of planetary encounters. The trajectory that brings the object within observation range of Mars, through optimal solar heating at perihelion, past Earth at ideal viewing distance, and finally through Jupiter's magnetosphere, represents a level of precision that Loeb argues is inconsistent with random gravitational mechanics. Drawing parallels to human space exploration, Loeb notes that 3I Atlas's trajectory bears striking similarities to paths designed for our own interstellar probe missions. Projects like Voyager and Pioneer demonstrated humanity's willingness to send reconnaissance probes beyond the solar system, and theoretical studies by NASA and other agencies have calculated optimal trajectories for hypothetical missions to nearby star systems. Many of these theoretical paths share characteristics with 3I Atlas's actual route. Loeb's hypothesis suggests that 3I Atlas might represent a sophisticated example of what he terms archaeological astronomy, the detection of technological artifacts from other civilizations through astronomical observations. Just as terrestrial archaeology reveals past civilizations through their material remains, Loeb argues that advanced civilizations throughout the galaxy might leave technological signatures that could be detected through careful analysis of unusual astronomical phenomena. The camouflage aspect of Loeb's hypothesis addresses one of the most common criticisms of artificial origin theories. Why would an advanced civilization go to such lengths to disguise their technology? Loeb suggests several possible explanations ranging from scientific ethics, avoiding contamination of primitive civilizations, to strategic considerations, reconnaissance without revealing the observer's capabilities or origins. Loeb also addresses the composition analysis of 3I Atlas, suggesting that the detected water ice and organic compounds might represent either genuine ancient materials incorporated into the probe's construction or sophisticated biomimicry designed to fool spectroscopic analysis. He notes that an advanced civilization capable of interstellar travel would likely possess the technological sophistication to create artificial materials with any desired chemical and isotopic signatures. The timing of 3I Atlas's arrival in our solar system also features in Loeb's analysis. He points out that the object's discovery comes during a period of rapid technological advancement for humanity, including the deployment of increasingly sophisticated space telescopes and the beginning of serious efforts toward interstellar communication and travel. This timing might not be coincidental if 3I Atlas represents a reconnaissance mission designed to assess our technological development. Critics of Loeb's hypothesis argue that he consistently favors exotic explanations over more mundane alternatives, a tendency that some colleagues suggest undermines his scientific credibility. They point out that extraordinary claims require extraordinary evidence, and that the anomalous characteristics of 3I Atlas, while unusual, fall within the range of natural phenomena observed elsewhere in the universe. However, Loeb counters that the scientific method requires considering all possible explanations for observed phenomena, including those that might seem uncomfortable or unlikely. He argues that dismissing artificial origins a priori represents a form of anthropocentric bias that could prevent us from recognizing genuine signs of extraterrestrial intelligence. Known. Dr. Avi Loeb has proposed that 3I Atlas exhibits characteristics consistent with artificial construction. Unknown. Whether Loeb's hypothesis will be supported by further observations or ultimately refuted. As 3I Atlas continues its journey, the debate over its origins intensifies. Part 14. The Mainstream Scientific Perspective. What if the mysteries of 3I Atlas have natural explanations? While the hypothesis of artificial origins for 3I Atlas has captured public imagination and sparked speculation, the vast majority of professional astronomers remain firmly convinced that the object represents a natural, albeit unusual example of an interstellar comet. This scientific consensus rests on decades of experience with solar system objects, theoretical understanding of planetary formation processes, and a methodical approach to evidence evaluation that prioritizes mundane explanations over extraordinary claims. The principle of Occam's razor plays a central role in mainstream scientific analysis of 3I Atlas. This logical tool, which suggests that the simplest explanation consistent with observed data is most likely to be correct, strongly favors natural origins for the object, while artificial construction could theoretically explain all of 3I Atlas's unusual characteristics. Such an explanation requires assuming the existence of advanced alien civilizations, sophisticated interstellar technology, and motivations for reconnaissance that remain entirely speculative. Natural explanations, while requiring some unusual circumstances, rely only on processes and materials that are known to exist throughout the universe. Large objects can be ejected from planetary systems through gravitational interactions with massive planets or stellar companions. Pristine compositions can be preserved during long interstellar journeys. Statistical improbabilities, while rare, must occasionally occur in a galaxy containing hundreds of billions of star systems and countless opportunities for unlikely events. Dr. Alan Fitzsimmons of Queen's University, Belfast, a leading expert on small solar system bodies, represents the mainstream scientific perspective on 3I Atlas. In his analysis, the object's characteristics, while unusual, fall within the range of natural phenomena observed elsewhere in the solar system and beyond. The size, while unprecedented for interstellar objects, is not unprecedented for comets in general. Several comets in our own solar system exceed 3I Atlas in diameter, including Comet Hale-Bopp and the Centaur Chiron. The composition of 3I Atlas, featuring pristine water ice and organic compounds, aligns perfectly with theoretical predictions for objects formed in the outer regions of other planetary systems. Computer simulations of planetary formation consistently show that such regions should produce objects with exactly the characteristics observed in 3I Atlas: large size, low density, high volatile content, and minimal thermal processing. The trajectory. Anomalies that have sparked so much speculation are addressed by mainstream astronomers through careful statistical analysis and gravitational modelling. Dr. Marco Micheli of the European Space Agency's Space Situational Awareness Programme points out that while 3I Atlas's trajectory is indeed statistically unusual, it's not impossible. In a galaxy with hundreds of billions of stellar systems and countless gravitational interactions, extremely improbable events must occasionally occur. Furthermore, selection bias might be influencing our perception of the trajectory's improbability. We naturally pay more attention to objects that pass close to Earth and other planets, making such trajectories seem more common than they actually are. Objects with less favorable trajectories might pass through our solar system undetected or with minimal scientific attention, creating an observational bias toward seemingly designed paths. The missing cometary signatures that have puzzled some observers are explained by mainstream scientists as a natural consequence of the object's thermal history and composition. Dr. Geraint Jones of the Mullard Space Science Laboratory notes that different comets begin outgassing at different distances from the Sun depending on their specific composition and thermal properties. Some comets, particularly those with unusual compositions or thick surface crusts, remain inactive until very close solar approaches. The interstellar origin of 3I Atlas might actually make delayed activation more likely rather than less. Objects that have spent millions of years in interstellar space have been subjected to cosmic ray bombardment and interaction with interstellar material that could modify their surface properties. These modifications might create insulating layers or alter surface chemistry in ways that delay the onset of cometary activity. Mainstream scientists also point to the successful detection of water ice and organic compounds in 3I Atlas as evidence against artificial origins. If the object were an artificial probe, why would its creators go to the effort of incorporating genuine, interstellar materials with authentic isotopic signatures? It would be much simpler to construct a probe from artificial materials that merely appeared natural from a distance. The isotopic signatures detected in 3I Atlas, while different from solar system materials, are entirely consistent with formation in a different stellar environment. Variations in stellar metallicity, age, and evolutionary history naturally produce different isotopic ratios in condensed materials. The specific signatures observed in 3I Atlas match theoretical predictions for objects formed around stars with different characteristics from our Sun. Known. Mainstream scientists favor natural explanations for 3I Atlas's characteristics. Unknown. Whether these explanations will hold as more data is gathered during its upcoming flybys. As 3I Atlas approaches perihelion, the debate between natural and artificial origins continues. Part 15. The Legacy of Oumuamua. What if our first interstellar visitor was more than it seemed? The story of Oumuamua, our solar system's first confirmed interstellar visitor, provides essential context for understanding current debates about 3I Atlas and the challenges of interpreting anomalous astronomical observations. Discovered on October 19, 2017, by astronomer Robert Werrick using the Panoramic Survey Telescope and Rapid Response System PAN-STARRS in Hawaii, Oumuamua immediately presented puzzles that continued to challenge conventional understanding of interstellar objects. The discovery process itself was routine initially. PAN-STARRS, designed to scan the sky for potentially hazardous asteroids, detected a faint moving object that initially appeared to be just another near-Earth asteroid requiring standard follow-up observations. Only after several nights of tracking did astronomers realize they had spotted something extraordinary, an object on a hyperbolic trajectory that had originated from outside our solar system. The name Oumuamua, chosen by the PAN-STARRS team in consultation with Hawaiian language experts, means messenger from afar arriving first, in Hawaiian. This poetic designation proved prophetic, as the object would indeed deliver messages about the nature of interstellar space and challenge our assumptions about what visitors from other star systems might look like. The initial observations of Oumuamua revealed an object unlike anything previously seen in our solar system. Photometric measurements suggested an extremely elongated shape with a length-to-width ratio of approximately 10.1, resembling a cosmic cigar or needle more than the roughly spherical shapes typical of asteroids and comet nuclei. This unusual geometry immediately sparked scientific interest and speculation about the object's origins and formation mechanisms. Even more puzzling was Oumuamua's surface properties. The object exhibited unusually high reflectivity, with an albedo roughly 10 times higher than typical comets and asteroids. This mirror-like quality, combined with a reddish coloration similar to objects in the outer solar system, suggested a composition unlike typical space rocks. The high reflectivity was particularly difficult to explain, as most objects in space develop dark, carbon-rich surfaces due to space weathering processes over geological timescales. Perhaps most mysteriously, Oumuamua showed no signs of the cometary activity that astronomers expected from an object originating in interstellar space. As it approached and rounded the Sun, the object exhibited no visible coma or tail, no detectable gas emissions, and no dust production that could be observed with even the most sensitive instruments. The mystery deepened when careful astrometric measurements revealed that Oumuamua was experiencing a small but measurable non-gravitational acceleration away from the Sun. This acceleration was too large to be explained by solar radiation pressure alone, yet it occurred without any detectable outgassing that could provide rocket-like propulsion through sublimation. The acceleration followed a precise mathematical relationship with solar distance, decreasing as the object moved away from the Sun in exactly the pattern expected from solar radiation pressure, but with a magnitude far too large for an object of Oumuamua's estimated mass and size. Dr. Marco Micheli of ESA's Space Situational Awareness Program led the team that discovered this anomalous acceleration through painstaking analysis of positional measurements from multiple observatories. The acceleration was subtle, approximately 5x 10 ISDs 6 meters per second squared, but persistent and clearly detectable above measurement uncertainties. This finding, published in Nature in June 2018, opened the door to numerous competing explanations for Oumuamua's behavior. The mainstream scientific community proposed several natural explanations for the mysterious acceleration. The leading hypothesis suggested that Oumuamua was undergoing extremely subtle outgassing that was invisible to current detection methods. This stealth outgassing might involve hydrogen gas produced by water ice sublimation, which would be virtually impossible to detect spectroscopically, but could provide sufficient thrust to explain the observed acceleration. Alternative natural explanations included the possibility that Oumuamua was composed of unusual materials that could explain both its high reflectivity and anomalous acceleration. Some researchers suggested the object might be a fragment of solid hydrogen formed in the extremely cold environment of interstellar space. Others proposed that it might consist of exotic ices or organic compounds with unusual thermal properties. The most detailed natural explanation, developed by Dr. Darrell Seligman of Yale University and others, suggested that Oumuamua represented a dark comet, an object that had lost most of its volatile materials during previous close. Approaches to stars, leaving behind a core capable of limited outgassing under intense solar heating. This model could explain both the lack of visible cometary activity and the subtle acceleration, though it required assuming a complex thermal and outgassing history. However, it was Dr. Avi Loeb of Harvard University who proposed the most controversial explanation for Oumuamua's anomalous properties. In a paper co-authored with Dr. Shmuel Bialy, Loeb suggested that the object's extreme elongation, high reflectivity, and solar radiation pressure acceleration were all consistent with artificial construction, specifically a light sail manufactured by an extraterrestrial civilization. Loeb's light sail hypothesis addressed multiple anomalies simultaneously. The extreme elongation could result from engineering requirements for an efficient solar sail. The high reflectivity would be essential. For maximizing radiation pressure effects, the precise relationship between acceleration and solar distance matched theoretical predictions for light sail behavior. Most importantly, the hypothesis could explain why the object showed acceleration consistent with outgassing without any detectable gas emissions. The scientific community's reaction to Loeb's hypothesis was swift and largely negative. Critics argued that extraordinary claims required extraordinary evidence, and that Oumuamua's properties, while unusual, could still be explained through natural processes that didn't require invoking alien technology. The peer review process subjected Loeb's papers to intense scrutiny, and while they were eventually published in reputable journals, most astronomers remained unconvinced. NASA's Spitzer Space Telescope played a crucial role in the Oumuamua investigation by providing negative results that were almost as important as positive detections. Spitzer's sensitive infrared observations failed to detect the object during its outbound journey, providing upper limits on its size and thermal emission that constrained theoretical models. These observations suggested that Oumuamua was smaller than initially estimated and had a lower thermal emission than expected for a typical asteroid or comet. The Spitzer non-detection also supported more exotic explanations for the object's nature. If Oumuamua were indeed a thin, highly reflective light sail, it might be too small and cool to detect with infrared telescopes, consistent with the Spitzer observations. However, the same result could also support natural explanations involving unusual composition or structure. As Oumuamua continued its outbound journey, it gradually faded beyond the detection limits of even the most powerful telescopes, leaving behind a wealth of observational data but no definitive answers about its true nature. The object's brief passage through our solar system demonstrated both the incredible capabilities of modern astronomy and the limitations of studying objects that provide only fleeting observation opportunities. The lessons learned from Oumuamua have proven invaluable for studying subsequent interstellar visitors like 3I Atlas. The scientific community developed improved observation protocols, theoretical frameworks, and data analysis techniques that are now being applied to the current visitor. Most importantly, the Oumuamua experience highlighted the need for rapid response capabilities and comprehensive observation campaigns when dealing with transient interstellar objects. The debate surrounding Oumuamua also established important precedents for evaluating claims about potential extraterrestrial technology. The scientific community's cautious approach to Loeb's hypothesis demonstrated both the importance of considering all possible explanations and the need for rigorous evidence standards when evaluating extraordinary claims. Looking back at the Oumuamua case from the perspective of 2025, several key insights emerged that inform current discussions about 3I Atlas. First, interstellar objects can exhibit properties that challenge conventional understanding without necessarily being artificial. Second, the absence of expected phenomena like cometary activity can be as scientifically significant as their presence. Third, statistical arguments about improbable characteristics must be evaluated carefully within the context of selection biases and observational limitations. The Oumuamua experience also demonstrated the value of maintaining multiple competing hypotheses throughout the observation and analysis process. While most scientists ultimately favored natural explanations, the ongoing debate encouraged more thorough investigation of the object's properties and led to discoveries that might otherwise have been overlooked. Perhaps most importantly, Oumuamua showed that the universe still holds surprises that can challenge our theoretical understanding. The object's unique combination of properties, extreme elongation, high reflectivity, anomalous acceleration, and lack of cometary activity had never been predicted by theoretical models of interstellar objects. This humbling experience reminded astronomers that nature often exceeds the boundaries of human imagination and theoretical frameworks. Known, Oumuamua exhibited anomalous properties that challenged conventional explanations. Unknown, whether 3I Atlas will ultimately prove to be as enigmatic as its predecessor. As 3I Atlas continues its journey, the lessons of Oumuamua loom large. Part 16. Project Lyra and the Future of Interstellar Missions. What if humanity's next great leap is to the stars? In the aftermath of Oumuamua's discovery and the tantalizing mysteries it left in its wake, the international space community began seriously considering unprecedented missions to intercept and study interstellar objects. The most ambitious of these concepts was Project Lyra, a theoretical mission designed to catch up with Oumuamua and conduct detailed in situ analysis of humanity's first confirmed interstellar visitor. Project Lyra emerged from collaboration between researchers at the European Space Agency's Advanced Concepts team and scientists at institutions worldwide. The project's name, derived from the constellation Lyra, where Oumuamua's trajectory suggested it might have originated, captured both the poetic and scientific significance of attempting humanity's first interstellar chase mission. The technical challenges facing Project Lyra was staggering. By the time serious mission planning began in 2018, Oumuamua was already racing away from the Sun at speeds exceeding 26 kilometers per second. Catching up with an object moving at such velocities would require spacecraft technologies that pushed the boundaries of current capabilities, including advanced propulsion systems, sophisticated navigation algorithms, and autonomous operation over interstellar distances. Initial trajectory. Analysis revealed that a conventional chemical rocket mission to Oumuamua was impossible with existing technology. The energy requirements for matching the object's velocity exceeded the capabilities of any launch vehicle ever built. Even using gravitational assists from multiple planets, a spacecraft would need to achieve velocity changes far beyond the reach of traditional propulsion systems. The Project Lyra team therefore focused on advanced propulsion concepts, including solar sails, ion drives, and even theoretical fusion rockets. Solar electric propulsion emerged as the most promising near-term option, using efficient ion thrusters powered by large solar arrays to gradually accelerate a spacecraft over periods of years or decades. While such a mission would take an extremely long time to reach its target, the scientific payoff from direct analysis of interstellar material justified. The extended timeline. Dr. Andreas Hein of the Initiative for Interstellar Studies led detailed feasibility studies that mapped out the potential mission architectures for reaching Oumuamua. These studies revealed that even with the most optimistic assumptions about future propulsion technology, a mission launched in the early 2020s wouldn't reach the object until the late 2040s or early 2050s. By that time, Oumuamua would be so far from the Sun that solar power would be marginal, requiring nuclear power sources for spacecraft operation. The scientific instruments for a Project Lyra mission would need to operate reliably for decades in the harsh environment of interstellar space. Advanced spectrometers, imaging systems and sample collection devices would all need to function flawlessly after years of cosmic ray bombardment, extreme temperature cycling, and mechanical stress from constant acceleration. The mission would essentially require developing technology for true interstellar exploration, decades ahead of schedule. Communication with a Project Lyra spacecraft would present its own set of challenges. By the time the mission reached Oumuamua, the spacecraft would be hundreds of times farther from Earth than any previous interstellar mission. Radio signals would take hours to travel between Earth and the spacecraft, making real-time control impossible, and requiring unprecedented levels of spacecraft autonomy. The heat shield requirements for surviving close approach to an interstellar object also posed significant engineering challenges. At the relative velocities involved, even tiny dust particles become potentially destructive projectiles. The spacecraft would need sophisticated shielding systems capable of protecting delicate instruments from high-velocity impacts while maintaining the ability to collect and analyze samples of the target object. Despite these formidable challenges, Project Lyra generated significant interest within the space community. The European Space Agency included interstellar object missions in its long-term planning documents. NASA's Jet Propulsion Laboratory conducted preliminary studies of the technologies required for such missions. Private space companies began exploring whether their emerging capabilities might contribute to interstellar exploration efforts. The discovery of 3I Atlas in July 2025 has fundamentally changed the landscape for interstellar object missions. Unlike Oumuamua, which was discovered during its outbound journey, 3I Atlas was detected while still approaching the Sun. This advanced warning provides unprecedented opportunities for mission planning and potentially even rapid response missions using existing or near future technology. Dr. Petra Pokorny of NASA's Goddard Space Flight Center has led preliminary studies of potential missions to 3I Atlas, taking advantage of lessons learned from Project Lyra planning. The extended observation period before 3I Atlas reaches perihelion allows for detailed trajectory refinement, comprehensive mission planning, and potentially even the construction and launch of purpose-built spacecraft designed specifically for this opportunity. The trajectory of 3I Atlas, with its carefully orchestrated sequence of planetary flybys, presents unique opportunities for spacecraft missions. A probe launched to intercept the object during its Mars flyby could conduct detailed observations while the interstellar visitor is still relatively inactive. Alternatively, a mission designed to rendezvous with 3I Atlas during its Jupiter encounter could take advantage of the massive planet's gravitational field for trajectory adjustments and extended observation periods. The large size of 3I Atlas compared to Oumuamua also changes the mission requirements and opportunities. While the object's 7-mile diameter presents challenges for comprehensive mapping and analysis, it also provides a stable platform for extended observation and potentially even surface operations. A spacecraft equipped with landers or penetrators could conduct detailed subsurface analysis that would be impossible with smaller targets. Sample collection from 3I Atlas represents perhaps the greatest scientific opportunity in the history of space exploration. Direct analysis of pristine interstellar material could provide unprecedented insights into planetary formation processes in other star systems, the distribution of organic compounds throughout the galaxy, and potentially even signs of past or present life from other worlds. The technological requirements for a 3I Atlas mission, while still challenging, are significantly more achievable than those for Project Lyra. The object's approach trajectory allows for conventional launch windows and flight times measured in years, rather than decades. Existing ion propulsion technology could potentially enable rendezvous missions, while advanced solar sails might allow for extended observation periods and sample return capabilities. International cooperation will be essential for any comprehensive 3I Atlas mission. No single space agency possesses all the technologies and resources required for such an ambitious undertaking. The mission would likely require contributions from NASA, ESA, JAXA, and other agencies, along with potential involvement from private space companies with advanced capabilities. The timeline for a 3I Atlas mission depends heavily on the level of ambition and international commitment. A simple flyby mission using existing technology could potentially be launched within 2 to 3 years, arriving at the target during its outbound journey in the late 2020s. More sophisticated rendezvous and sample return missions would require longer development times but could still reach the object while it remains within range of reasonable communication. And navigation systems. Known. The discovery of 3I Atlas has renewed interest in interstellar object missions. Unknown. Whether a mission to 3I Atlas will receive funding and approval in time to capitalize on this unprecedented opportunity. As 3I Atlas approaches perihelion, the future of interstellar exploration hangs in the balance. Part 17. The Final Countdown. What if the fate of 3I Atlas decides humanity's cosmic destiny? As 3I Atlas approaches its final milestones, perihelion on October 29, 2025, the Earth encounter on December 19, 2025, and the Jupiter flyby on March 16, 2026, the world watches with bated breath. These encounters will provide unprecedented observational opportunities, potentially revealing the object's true nature and reshaping our understanding of the cosmos. But time is running out. After its Jupiter flyby, 3I Atlas will begin its final departure into interstellar space, gradually fading from view as it moves beyond the reach of even our most powerful telescopes. The decisions made in the coming months and years will determine whether humanity seizes this unprecedented opportunity to directly study material from another star system, or watches helplessly as our third interstellar visitor fades into the cosmic distance, taking its secrets with it. The scientific community is prepared for whatever revelations 3I Atlas may bring. Ground-based and space-based observatories are ready to monitor the object during its perihelion passage, searching for signs of cometary activity or unusual emissions that might indicate artificial origins. The James Webb Space Telescope and the Vera C. Rubin Observatory will play central roles in these observations, using their unprecedented sensitivity to analyze the object's composition and behavior. Radio telescopes will search for any electromagnetic emissions that might indicate active electronic systems, while spacecraft positioned at the L1 Lagrange point and in Mars orbit will provide uninterrupted coverage during the critical perihelion period. But the scientific community is not alone in its preparations. Space agencies around the world are exploring potential missions too. Intercept 3I Atlas, taking advantage of the advanced warning provided by its approach trajectory. NASA, ESA, JAXA and other agencies are conducting feasibility studies for flyby, rendezvous, and even sample return missions. Private space companies are also expressing interest in contributing to these efforts, leveraging their emerging capabilities to push the boundaries of current technology. The technological legacy of projects like Lyra and Breakthrough Starshot is evident in these discussions as the space community builds on past efforts to develop new mission architectures and propulsion systems capable of reaching 3I Atlas in time. The timeline for a potential mission is tight but achievable. A simple flyby mission using existing technology could potentially be launched within 2 to 3 years, arriving at the target during its outbound journey in the late 2020s. More sophisticated. Rendezvous and sample return missions would require longer development times, but could still reach the object while it remains within range of reasonable communication and navigation systems. The scientific instruments for such a mission would build upon decades of experience with comet and asteroid exploration, incorporating advanced spectrometers, imaging systems and sample collection devices designed to operate in the harsh environment of interstellar space. But the implications of a mission to 3i Atlas extend far beyond scientific discovery. Confirmation that the object represents natural interstellar material would provide unprecedented insights into planetary formation and evolution throughout the galaxy. Discovery of artificial components or technology would represent the most significant scientific discovery in human history, proving that we are not alone in the cosmos and raising immediate questions about the intentions and capabilities of its creators. Either outcome would fundamentally transform our understanding of our place in the universe, reshaping fields as diverse as astronomy, astrobiology, philosophy, and religion. As 3i Atlas continues its journey through our solar system, it serves as a cosmic wake-up call, reminding us of the profound mysteries that lie beyond our planetary neighborhood. The discovery of 3 confirmed. Interstellar objects within less than a decade provides astronomers with an unprecedented opportunity to compare and contrast the characteristics of visitors from other star systems. Each object, Oumuamua, Borisov, and now 3i Atlas, exhibits distinct properties that collectively begin to define the range of phenomena we might expect from interstellar material, while also highlighting the unique characteristics that make each visitor scientifically valuable. The comparison between these 3 visitors provides valuable guidance for interpreting future interstellar object discoveries. The range of sizes, compositions, and behaviors observed suggests that interstellar space contains a diverse population of objects with varying origins and characteristics. Some, like Borisov, may represent relatively straightforward examples of natural cometary material. Others, like Oumuamua, and possibly 3i Atlas, may challenge conventional understanding and require new theoretical frameworks. The progression from Oumuamua through Borisov to 3i Atlas also demonstrates the rapid advancement in our ability to study interstellar objects. Each successive visitor has been observed with more sophisticated instruments, better theoretical understanding, and more comprehensive observation campaigns. This technological and methodological progress ensures that future interstellar visitors will be studied with unprecedented detail and precision. The 3 confirmed interstellar objects also provide the beginning of a statistical sample that allows for meaningful analysis of interstellar object populations. While 3 objects constitute a very small sample size, they already suggest significant diversity in the types of material traveling between star systems. Future discoveries will gradually build this statistical foundation and enable more robust conclusions about the frequency, characteristics, and origins of interstellar visitors. Perhaps most importantly, the comparison between Oumuamua, Borisov, and 3i Atlas demonstrates that each interstellar visitor is likely to be unique in some respect, requiring individualized study approaches and open-minded interpretation of observational data. The universe appears to be far more diverse and surprising than theoretical models predict, ensuring that each new interstellar discovery will contribute unique insights to our understanding of planetary formation, stellar evolution, and the cosmic processes that connect star systems throughout the galaxy. As 3i Atlas approaches perihelion, the world watches and waits. Will this enigmatic visitor reveal itself as a natural interstellar comet, a sophisticated alien probe, or something else? Entirely. The answer may lie in the data gathered during its upcoming flybys and perihelion passage. But regardless of the outcome, 3i Atlas has already transformed our understanding of the cosmos and our place within it. It reminds us that the universe is far stranger and more wonderful than we often imagine, and that the next great discovery in astronomy might arrive without warning, disguised as just another faint point of light moving against. The stars. Known. 3i Atlas will reach perihelion on October 29th, 2025, and begin its final departure from our solar system after its Jupiter flyby on March 16th, 2026. Unknown. Whether humanity will seize this unprecedented opportunity to directly study material from another star system or watch as 3i Atlas fades into the cosmic distance, taking its secrets with it. As 3i Atlas completes its grand tour of our solar system and departs. Into the cosmic dark, it leaves us with the most tantalizing question in human history. Are we witnessing first contact through the Black Forest's silent watchers, or simply the universe's most remarkable coincidence? The answer may shape the future of humanity and our place among the stars.